Let's talk about some other interesting places in the solar system where there could be life, or at least habitable environments. Now, one unusual place is the moon of Neptune, called Triton. Triton is an unusual moon because it orbits backwards around Neptune, and this has led to the idea that maybe it was a body that was captured by Neptune early in the history of the solar system. Like Europa, it has an icy surface, but Triton seems to have a surface that also contains nitrogen, methane, carbon dioxide, carbon monoxide, and other types of volatile compounds that are frozen down onto the surface of the moon. But it's another example of an icy moon in the outer solar system. There are some parts of this moon that have a lot of impact craters, and that suggests that those areas might be quite old. But generally, the surface of Triton seems to be very young. And in fact, there are locations on the surface of the moon where there seems to be active geological processes, particularly black colorations on the surface that look like nitrogen geysers erupting from the subsurface of the moon, suggesting some sort of cryoactivity beneath the surface where nitrogen is welling up through fractures and being ejected onto the surface of the moon. So although the surface of Titan looks like it has some activity today, generally speaking, the surface of the moon doesn't look as active as, for example, Europa. But that might have been very different in the early history of the moon. In the early history of the solar system, it's possible that Triton was tidally flexed, a bit like Europa, and it's possible that in the subsurface of that moon, there may even have been a subsurface liquid ocean. Is it possible that this moon was habitable in its early history? Is it even possible that today there might be pockets of habitable environments in the subsurface of the moon? Well, we don't really know enough about Triton to be able to assess those ideas accurately, but this is certainly another place in the solar system where we might think about searching for habitable conditions, and a place that may even have had habitable conditions in the early history of the solar system. And one can imagine studying the surface of that moon, looking at the compounds on the icy surface, perhaps even looking for biosignatures of life that might have once lived in the subsurface of Triton. So this is another example of a moon far away from the sun that could have had habitable environments because of tidal forces within the moon. We talked a little bit about Europa, perhaps one of the most compelling locations to search for habitable environments amongst the icy moons of the solar system. Another moon of Jupiter that might be worth investigating is Ganymede. And Ganymede, like Europa, also seems to have a subsurface liquid ocean. This is an image showing you a slice through Ganymede and what we think the internal structure of that moon looks like. It's probably got a metallic core surrounded by a rocky inner mantle, a rocky core, silicate core around the metallic core. And then beyond that, a shell of warm ice. And then just above that, a liquid water ocean. And that ocean is trapped between that warm ice beneath it and the icy crust on the surface of the moon, a bit like the icy crust of Europa. So that liquid water ocean in Ganymede could also be another location where we could look for habitable conditions. But there is one problem with that ocean, and that's that it's trapped between two layers of ice. And as we saw earlier in this course, life needs a lot of things to get going. It needs elements, it needs a source of nitrogen and phosphorus, and certain elements like iron to do chemical reactions. An ocean that's in contact with a silicate core, a rocky core like Europa, might be a much better place for life because it'll have more of an enriched collection of elements and potential nutrients and even energy supplies for life. But an ocean that's trapped between two layers of ice might be very limited in the quantities of nutrients and elements that it has. So perhaps Ganymede isn't such a good location to search for life as, say, compared to Europa. But nevertheless, any environment in the solar system where there's liquid water could be a potential habitable environment. So Ganymede is another moon that we might look at as a potential location for life, and if not life, then perhaps some of the early chemical reactions that might suggest habitable environments where there is potential for life. People have had even more crazy ideas. The possibility of habitable environments around Pluto and its moon Charon. And in 2015, the New Horizons mission will arrive at Pluto and give us some ideas about the composition of that body and also its moon Charon. Is it possible that these bodies also have subsurface oceans? Well, we don't know enough about them to be able to speculate with any accuracy on that. But we might even look for habitable environments beyond the orbit of Neptune. And this just illustrates the remarkable possibilities for liquid water habitats in our solar system. We've looked at Europa, Ganymede, even the moon of Neptune, Triton, and possibly we might even look for habitable environments in the subsurface of bodies beyond that, Pluto and Charon. But there is one moon I want to return to in this lecture, and that is Titan, one of the moons of Saturn, in fact the largest moon of Saturn. It's an intriguing moon, and strangely enough, when people first looked at this moon, it didn't look very interesting. This is an image of Titan, and you can see that it's got this homogeneous haze that covers the surface of this moon. It doesn't look like it has many interesting features. But it turns out that this haze is a very fascinating atmosphere. This haze is a mixture of nitrogen and hydrocarbons, methane and other carbon compounds of great interest to astrobiologists. And in fact, it's really the only place beyond the Earth where stable bodies of liquids exist on the surface of that moon. What are these liquids and what are the characteristics of this moon that make it so interesting to astrobiologists? Well, in 2005, the Cassini spacecraft let go of the Huygens lander that travelled down to the surface of Titan and sent us back the first images of the surface of that moon. And you can see an image here, a remarkable image of the surface of Titan that was taken by the Huygens lander. What did it see? Well, it saw what looked like rocks, and you can see these rocky formations on the surface of Titan. But it turns out that these are not rocks. These are lumps of ice, solid water ice that behaves like rock at the very low temperatures to be found on the surface of Titan. But what it also found was landscapes made of hydrocarbons, complex organic carbons that forms from this complex atmospheric process that occurs on Titan. You see, Titan has lakes of liquid methane and ethane that formed over the surface of the moon. This methane evaporates into the atmosphere of Titan. It rises up into the atmosphere, and then it reacts with ultraviolet radiation from our sun. And that ultraviolet radiation causes the methane to react and form complex organic carbons. That brown haze that you see in the atmosphere of Titan is actually complex organic material formed from the reaction of methane and other organic compounds with ultraviolet radiation from the sunlight. And these complex organic carbons rain down to the surface of Titan and form these landscapes of complex carbon compounds. And that is what you're looking at here in this image taken by Huygens, looking out across the surface of Titan, across these hydrocarbon landscapes. Why is this so interesting to astrobiologists? Well, these complex organic reactions of carbon compounds with ultraviolet radiation, might be the sort of reactions that occurred on early Earth that ultimately led to the origin and evolution of life. Could we learn something about how life comes to be, how the building blocks for life are formed, by looking at these complex organic carbon reactions that are occurring in the atmosphere and the surface of Titan? So we can think of Titan as a laboratory for understanding complex organic carbon chemistry that might tell us something about how life originates and how the building blocks for life originate in planetary environments. So it's a very, very fascinating environment for astrobiologists. And quite apart from that, we can also learn something about the incredible geology of a moon where mountains are carved by liquid methane, not liquid water, but liquid methane. What do rivers of liquid methane do to landscapes? And how do they form this unusual network of mountains and valleys that we observe on the surface of Titan? One day we might even send probes to land in these lakes and rivers and follow their flow of these rivers and map out the movement of methane across these moons and take photographs of these incredible liquid methane environments. But quite apart from the surface of Titan, it also turns out that this is a very interesting moon in its subsurface as well. This is a cross-section through the moon, and it gives you some idea of what we think is going on beneath that fascinating surface where all that organic chemistry is occurring. And let's just look at those layers from the outside in. So we have this organic-rich atmosphere and surface that we've just talked about, that atmosphere that gives it that brown organic haze. And then just beneath that, we've got an ice layer, a solid water ice layer, and clathrate, which is a sort of caged ice material just beneath the surface of Titan. And then beneath that, there may be a liquid water ocean, a bit like Europa and Ganymede. But this liquid water ocean may also contain ammonia. We might be looking here at an ocean that's actually a mixture of liquid water and ammonia. And then just beneath that, a layer of high pressure ice, unusual ices at very high pressures that form unique crystalline structures, possibly ice 6 and other types of unusual icy structures. And then beneath that, a rocky core, much like other moons, a classical rocky core made up of silicates. So what we've got here is a very, very unusual moon with a classic rocky core, but above that, strange layers of ice, perhaps subsurface water oceans, water ammonia oceans, and then on the surface of that, that unusual organic chemistry that we can see directly with our space programs. Why is this of interest to astrobiologists? Well, I've mentioned the interest in the surface environment for understanding organic chemistry. We might ask questions like, if there is a subsurface water ammonia ocean in the subsurface of Titan, could it be a location for life? Could it be a place where life originated? Could we even get samples of that ocean? That would be a very difficult thing to do, but we could start to ask questions about habitable environments in the subsurface of that moon. So for a whole range of angles, Titan is of interest to astrobiologists. As we go from the surface, we've got organic chemistry that might tell us something about the origin of life and where the building blocks of life come from. As we go into the subsurface, we have a liquid water, ammonia ocean that might tell us about possible habitable environments for life. It may even be a location to look for life today. And then beneath that, the rocky cores of these icy moons tell us something about how these moons formed and how they may have led to habitable conditions. So very briefly, that's a snapshot of some of the other environments in the solar system where we might learn something about the origin of life and also even look for habitable environments today. It just shows you that you should make no assumptions about where habitable environments might be. Some apparently very hostile places, from Titan to Triton and Ganymede, can have surprises beneath their surfaces, liquid water that might be places for habitable conditions. So what have we learned in this lecture? Well, we've learned that there are a number of possibilities for life in icy bodies in the solar system. We've looked in this lecture course at Europa and Enceladus. In this lecture, we see that there are a multitude of other planetary bodies that could be places where we could carry out astrobiological investigations. We've also learned that much of this speculation revolves around the idea of liquid water. And we saw how earlier on in this lecture course, liquid water is essential for life as we know it. So that is the essential ingredient in all of this discussion and speculation. Any moon where there's liquid water could be a place where we might hypothesize habitats for life. It certainly might be places worth investigating as places for life. Even if it's not there, we'll learn something about conditions for habitable locations elsewhere in the universe. And we've also learned that there are places where we can learn about unusual parts of astrobiology, like the origin of life, the surface of Titan, organic chemistry, and complex organic chemistry. So in that brief collection of unusual moons, we can see how there is a vast range of information for astrobiologists to go out and explore in the coming years.